In this video, we'll learn about evaluation metrics used for classification problems. Before we dive into that, it will be helpful to define a formal way of representing the values predicted by our classification model and the actual values in the dataset. This will add a lot more clarity to our evaluation process. For this purpose, we use a confusion matrix. The word confusion might be there in the name, but don't worry. It's easy to grasp when you understand the intuition behind a confusion matrix. So let's begin. A confusion matrix is a n by n matrix where n represents the number of classes in the variable. In the Titanic dataset, our dependent variable had only two classes, 1 and 0, representing survived and not survived respectively. Therefore, in this case, the value of n will be 2, and the confusion matrix formed will be a 2 by 2 matrix. Note that there can be multiple classes in the dependent variable, but for this video, we are only going to use a 2 by 2 matrix or a binary matrix for easier understanding of the concept. Now, each row in this matrix represent the actual class values and the columns represent the predicted classes. Each row represents a class under the actual value and each column represents the class under the predictive value. Each cell holds some value and each of these cells represents some meaning that also decides the name of a particular cell. Let's discuss this in a bit more detail. Let's take a step back and first focus on the values predicted by our model. As this is a binary classification problem, the model can only predict two values, positive and negative, or as you can say 1 and 0. If we look at this column on the left, this column represents the values predicted positive by the model. Therefore, let us write P on those cells. So here it is. Similarly, the column on the right represents the values predicted as negative by our model. Once that's done, the next step is to check the predicted values against the actual values. The observed or actual value in our dataset can either be positive or negative, right? Since this is a binary classification problem. Now consider that the classification model predicts the value as positive, which implies that we are in the left column. So we need to check whether the values predicted by our model are actually positive. Let's say the value predicted by my model is 1 and the actual value is also 1. So in this case, the predicted value is correct or true. So in the cell positive, we can write T. Now if the value predicted as positive by the classification model, but actually the value is negative, in this case the prediction is incorrect, or we can say false. So in this cell we can write false since the model has predicted positive but actually the value is negative. So here are the names of these two cells. Similarly, the question comes, are the values we predicted as negative actually negative? If yes, then we can say that the model predicted negative, the actual value is negative, so the prediction is correct or true. On the other hand, if the model predicted negative, but the actual value is positive, I can say the prediction is incorrect or false. So the total number of actual positive values is given by true positive and false negative, while the total number of actual negative values are given by false positive and true negative. Now that we have understood the notation, what they mean, and how to write them, let us solve an example to solidify our understanding. I'll pull up the Titanic dataset again since we are quite familiar with it by now. Here we have a few examples from the actual dataset, and we know that whether the passenger on the Titanic has survived or not, the values are given in the actual column. Now suppose we build a model and it produces these given predicted values, as in this column. Here comes the notations we learned in the video. In order to compute the confusion matrix, we'll first denote each observation. So for the first observation, the predicted value is 0, which means n, but the actual value is 1. So this prediction is incorrect or false. Similarly, for the second observation, the predicted value is 1, so positive, and the actual value is also 1. So this prediction is correct, or I can say true. Similarly, I can fill for all the observations, and here are the notations for all the observations. So what's next? count the number of true positives, false positives, true negatives and false negatives. We'll start by counting the true positives. So here I have 3 true positives. So I can write 3 in this cell. Now let's count the number of false negatives. So I have 2 false negatives here. So in this cell I will write 2. And the next, let's look at false positive. So I have only 1 false positive here. So in this cell I'll write 1. And now let us count the number of true negatives. So I have 1 and 2 true negatives here. So in this cell I can write 2. And there we are. Congratulations on building your first confusion matrix. Let's quickly recap what we have learned in this video. We saw what a confusion matrix is and how we can represent the predicted values against the actual values. We also covered what each of these notation means in the confusion matrix. So if we have the actual values as positive and the model correctly predicts it as positive, then I can say the prediction is correct and it will fall in true positive. Similarly, a correctly predicted negative class is labeled as true negative. The false positives represent those values which were mistakenly predicted as positive. And similarly, for the false negatives, these are the values which were actually positive but mistakenly predicted as negative. In this video, we also learned how to denote each observation on the predicted label and the actual label, and how to fill the confusion matrix using these notations. Now let's turn our focus to the first and most popular evaluation metric used for classification tasks, accuracy. To put a formal definition to accuracy, it is the ratio of the total number of correct predictions over the total predicted values. If we look at the confusion matrix that we studied previously, the true positives and the true negatives here are the correct predictions, which means were predicted positive by the model and are actually positive, or the values predicted negative by the model and were actually negative. So the accuracy can be denoted as the true positives plus true negatives, the corrected predictions, over total predictions. So the total predictions would include all these 4 values, right? So I can write accuracy as true positive plus true negative upon true positive, false negative, false positive plus true negative. Pretty straightforward, right? Let's take up an example to understand how accuracy works. Suppose there's a group of 500 people who undergo a cancer diagnostic test. 6 patients are tested positive. That is, it's detected that 6 of these people have cancer, whereas the other 494 were cancer-free. Intuitively, we can say that the patients suffering with cancer are very less in number as compared to the people who do not have cancer. So this is a classic example of imbalanced data. Now our job as data scientists is to build a predictive model that can predict whether a patient has cancer or not. This model would take inputs such as age, gender, previous medical history of the patient, the tumor size, the tumor color, and a lot other things. So let's assume we build a model and have a confusion matrix ready as shown here. Take a moment to parse through this. What's your first reaction? There are some big values and some small values in the confusion matrix. Our first intuition would be to calculate the accuracy of our model. Just plug in the values to this framework we defined previously. So I'll have here true positive as 4 and true negative as 486. So 4 plus 486 upon the total predictions. So that would be 4 plus 8 plus 2 plus 486, right? Now on calculating, the accuracy comes out to be 98%. Looking at the model accuracy, we can easily conclude that the model we made is performing extremely well, right? Well, not exactly. In order to understand why accuracy is not sufficient for this type of classification problem, let us consider another example, an example of a dumb model. So we again consider the same 500 people. But this time we build a dumb model which predicts negative for every patient every time. If we look at the confusion matrix for the dumb model, it will look something like this. We can see that the model has predicted all the values as negative. Now if we use the accuracy formula and input the values from the confusion matrix, we'll have 0 plus 494 upon all the values. So I'll have 0 plus 6 plus 494 again. Now if we calculate, the accuracy comes out to be 98.8%. What just happened? Did a dumb model manage to trump a predictive model? We simply used the way of brute force to predict every patient as negative. Or maybe the predictive model we trained is worse than the dumb model. That is not possible, right? In reality, using accuracy as an evaluation metric on unbalanced data is not a great idea, as we saw in the example here. In order to evaluate the classification model properly, we need to look closely at the confusion matrix to find some better alternatives. In this section, we'll take a closer look at the confusion matrix in order to find the alternatives to accuracy metric. We'll start with the true positive rate. So the true positive rate is defined as the values predicted as positive by the model, which were actually positive, versus the total actual positives. So looking at the confusion matrix, the true positive rate can be written as the true positive over TP plus Fn, the total actual positives. As you can see, this metric emphasizes on the true positives predicted by the model. So it can be used in case where the business objective is to focus on identifying the actual positives. Like out of the total positives in the data, what was the percentage of positives your model was able to identify correctly? Since higher value would mean more number of positives correctly identified, this metric indicates that higher the value, better the model. And the range of this metric varies from 0 to 1. Now the next metric which we will look at is the false negative rate. It is defined as the ratio of values predicted as negatives which were actually positive, so the false negative, over the total actual positives. So looking at the confusion matrix again, we can formulate the false negative rate as here. The false negative upon true positive plus false negative. Now this metric emphasizes on the false negative values, which means that where were we not correct in terms of predicting the positives in the data. So lower the FNR represents a better model. Next one is the true negative rate. Now it is very similar to the true positive rate, but the focus here is on the negative classes. So it is the ratio of the predicted negative values which were actually negative, so the true negatives, over the total actual negatives. So we can formulate this as true negative upon true negative plus false negative. Now here the focus is on the true negatives. So the total number of negative classes in the data which were correctly captured by the model are the true negatives. And the business objective of this metric would be to focus on identifying the actual negatives. So what percentage of negative values your model was able to correctly identify out of the total negative values in the data? This matrix again ranges from 0 to 1. The next we will see is the false positive rate. It's the ratio of values predicted as positive but were actually negative, so the false positives here, divided by the total number of negative values. So here the focus is on false positive. Now this metric also says that our model has wrongly classified the actual negative classes to positive classes. So lower the value of FPR, better is the model. Again the matrix ranges from 0 to 1. Now we see that we have derived 4 metrics from the confusion matrix. Let us discuss about each of them in brief. In any given model, the true positive rate is always desirable. So higher the value of true positive rate, better is the model, since we are focusing on the correctly predicted positive values. Also, lower the value of false negative rate, better is our model, since false negative rate signifies the error rate of the model. In case of true negative rate, the higher value of true negative rate is desired, since the true negative signifies the correctly predicted negative values. On the other hand, false positive rate is often desired to be tending towards 0, as it is an error on behalf of the model. So the lower the value of false positive rate, better is the model. Let us now revisit the dumb model again, where the model predicts every person as negative, that is, nobody has cancer. We remember that the accuracy of this model came out to be 98.8%. Now let us check how the model performs with our new defined evaluation metrics. Let us calculate the TPR. So using the values from this confusion matrix here, I can define TPR, the true positive, as 0 upon 0 plus false negative, which is 6. So this comes out to be 0. The true positive rate of the dumb model comes out to be 0. This means that the model is not performing well since it has not correctly identified any of the positive values. This model doesn't look good anymore, does it? Similarly, when we calculate the other metric, we can find that the false negative rate is 1, which means all the cancer patients were classified as negative, which is the worst possible model. The false positive rate is 0. This implies that the patients who do not have cancer were not misclassified. But again, this is not relevant to the context, since our focus is on identifying the patients who actually have cancer. And the true negative rate comes out to be 1. So all the patients who were not having cancer were correctly identified. But we just studied about 4 metrics, and one could easily ask, do I need to check all of them? Long answer short, we can check all of the above metrics, but it's not necessary to do so. Using a combination of 2 metrics often works best. For instance, aiming for the true positive rate and the true negative rate is enough. These 2 metrics remove the need of checking any other metrics. The other metrics can be used in a combination so as to validate the results and not relying on any single metric. But choosing the right metric for a model totally depends on the use case. Different domains require optimization for different metrics. For example, the cancer patient problem that we talked about, the focus was on identifying the positives correctly. So we should use the true positive rate as our evaluation metric. One should understand the business requirement, talk to the relevant people about what's important for business, and then select the right metric. It's now time to see some of the most common use cases in data science and the metrics we use in these scenarios. First up is the concept of precision. It is defined as the ratio of the values predicted as positives that were actually positives. So as we already know, these are the true positives over total predicted positives. So using the confusion matrix, we can write this as the true positives over all the predicted positives. So it includes true positive and the false positive. So here we have the formula for precision, true positive upon true positive plus false positive. We'll take up an example to get an intuition of this precision concept. So let's use the cancer detection problem since we are already familiar with the problem statement. We'll reconsider the predictive model we built earlier. Previously, the accuracy we obtained for this model came out to be 98%, and we discussed that accuracy is not the best metric in this case. Let us now calculate the precision metric for the same model. So using the formula we studied previously and the values from the confusion metric that we have here, I can write precision as 4 upon 4 plus 8, which comes out to be 33.33. Well, the model doesn't look so precise now, does it? Now that we have a basic idea about the evaluation metric precision, let's look at a case where we will need to use precision as the evaluation metric. In this example, you are a detective tasked with catching a group of criminals, and you know that those criminals are attending a party full of very important people. As you can imagine, declaring these important people as criminals can have dire consequences for your agency. So as a detective, you can only arrest the criminals. To be perfectly clear, avoiding the wrongful arrest of these VIPs takes precedence over catching these criminals. In order to do that, we must minimize the VIP we declare as criminals. So take a moment to ponder this. Avoiding arresting a VIP as a criminal is analogous to minimizing the false positives. But in order to minimize this false positive, it is essential to understand that there is a very high chance of a criminal escaping and not being caught. This means that the false negative value may increase. In a nutshell, precision is used when we cannot afford to have false positives, or avoiding false positives is more important than encountering false negatives. So I hope you now understand what is precision and what is the use case where precision can be used as an evaluation metric. Let us turn to the second evaluation metric we'll learn in this video, called recall. This is also fairly commonly used in the industry. Recall can be defined as out of total actual positive values, how many did the model predict as positive? Let us use the confusion matrix to understand this better. So we have the total actual positive values, which is the true positive, against the total positives. So that is true positive and false negative. So here is the formula for recall. Again, we'll take up an example to explore how recall works. So we'll evaluate the cancer detection model again. This time we'll use recall as a metric in mind. Let us input the values from the confusion matrix into the formula here. So I have 4 true positives plus 2 false negatives. So this comes out to be 66%. Again, the accuracy metric turned out to be misleading. Like we did for precision, I'm going to take up a use case to show how recall works in the real world scenario. Consider that you are at the airport and passing through the metal detector. The aim of the security is to catch all the people who are carrying weapons. In order to catch every person who is carrying a weapon, the security guard will check any person for whom the metal detector rings, irrespective of whether he or she is innocent or not. In other words, it is important to catch the weapon carrier than check an innocent person for weapons. If we look at the definition for recall, trying to catch every weapon carrier is analogous to minimizing the value of false negatives. That is, no weapon carrier should get by. The price of trying to catch all the weapon carriers leads to innocent people being checked by the security, which is analogous to high false positive rate. So in a nutshell, recall is used when we cannot afford to have false positives, or avoiding false negative is prioritized over encountering false positives. So we have learned both precision and recall. Now, is there any direct relation between them? Think about it for a moment. As you can see here, this happens to be the trade-off between the precision and recall. Note that this trade-off is often very small, for instance 70 to 90. So if we aim for very high precision, that is trying to strictly predict the true positives and avoiding false positives, there is a good chance that the false negatives will go higher. Therefore, the recall will drop to a lower value. Similarly, if we aim for a high recall that is trying to predict all the actual positives as true positives and avoiding false negatives, there's a good chance that the false positive will go higher. Therefore, the precision will drop to a lower value. Makes sense, right? I just want to reiterate that precision and recall are used in diverse cases, and prioritizing one over the other depends upon the use case. You might come across scenarios where prioritizing precision over recall or vice versa is not clear. In this case, they both can be combined in order to obtain a good model. That's right. The combined evaluation metric is known as F1 score. F1 score is the harmonic mean of precision and recall. Since we took the mean, it reaches its maximum value when precision is equal to recall. A point to note is that F1 score lacks interpretability, and therefore it is often used in combination with other evaluation metrics. So far we have covered the evaluation metrics which considered only deterministic outcomes like 1 and 0. But there are some classification predictive models which predict probabilities of classes rather than the class itself. These cannot be handled by the evaluation metrics we learned so far. We're quite familiar with this confusion matrix. We have seen how it works, how to interpret it, and we also derived various evaluation metrics from this, like the true positive rate, the false positive rate, true negative rate, and the false negative rate. Let's quickly review these metrics. So the true positive rate here is the ratio of correctly predicted positive values over the total actual positives. Similar to true positive rate, we have the true negative rate, which takes into account the correctly predicted negative values over the total actual negatives. Another metric that we saw was the false positive rate, which was the incorrectly predicted negative classes over the total actual negatives. And lastly, we have the false negative rate, which is the ratio of incorrectly predicted negative values over the total actual positives. Let us look at an example. Remember this table we used before? These are the sample observations taken from the Titanic dataset. Here we have the actual values, and we also have the predicted values for our model. Now we can use these predicted values to determine the true positives, false positives for each of the observation. So let's do that. I have 1 here which is a positive, and the actual value is also 1, so it is a true positive. Similarly for this it will be positive and the actual value is 0, so false positive, and so on and so forth. We can do it for all the rows. So as I've done here, now we can count the total number of true positives, false positives, true negatives, and false negatives. Once we have these numbers, we can use it to calculate the true positive rate and false positive rate. Let's quickly do that. So here I have 3 true positives. So I can write 3 here. And then for false negatives, I have 2 false negatives. So it comes out to be 3 by 5, which is 0.6. Again, if I want to calculate the false positive rate, I'll count the total number of false positives, which comes out to be 2. And the true negatives comes out to be 1. So I'll have this again as 0.66. So you can see how we can calculate true positive rate and false negative rate. Similarly, we can do it for the true negative rate and the false negative rate. I encourage you to pause the video and calculate these values at your end before moving ahead. So far, we used the predicted classes, which were 0 and 1. Now, what if I have a model that is predicting probabilities of classes and not the classes themselves? And suppose I want to use these probability values to understand how my model performs. We know that we can't really compare these probabilities with the actual classes, can we? So, is there any way to generate actual classes based on these probabilities for the classes? Think about it. Let's say I set a cutoff to 0.5. So, the probability values which are greater than 0.5 or equal to 0.5 can be labeled as 1, and the other probabilities which are less than 0.5 can be labeled as 0. So if I do this for this problem, I'll have 0.9 as 1, 0.51 is again greater than 0.5, so it will be 1. Then similarly this will be 0 and this will be 0 and so on. So once I do it for all the predicted probabilities, I will actually have the predicted classes. After obtaining the predicted classes, we know the steps, right? We can calculate which one of them is true positive, which is false positive, and so on. And using the count of the true positive, false positive, true negative, and false negative, we can generate the true negative rates, false negative rates, etc. You know the formulas to calculate these, right? In case you face any difficulty, I encourage you to watch the previous videos again. So moving forward, I can see that my model has predicted 4 out of 8 values incorrectly. For example, in the second ID, the predicted value is 1, but the actual value is 0. Similarly, here we have the predicted value as 0 and the actual as 1, and so forth for the ID 4 and ID 8. So, what can we do to improve the model's predictions? The first obvious solution would be to retrain the model, which we usually do. We can build a new model, calculate the new predictions, and then go ahead and calculate the TPR FPR rates. But is there any way we can use the same model? Can we play around with the threshold value? Remember, we set it to 0.5 currently. Now let's try and change the threshold value to 0.4 and calculate these actual values. So here I've done that. We can now see that I have only 3 incorrect predictions. Once we have these actual values, we can calculate the TP, TN, FP and FN. And if I have the total number of true positives and false positives, I can finally calculate the true positive rate, false positive rate, etc. using the formula we saw previously. So in our case, the true positive rate goes to 0.8. Previously, we had it 0.6. So I can see that the true positive rate has increased, which means I have predicted more number of positives correctly. Now let's play around with the threshold value a bit more. So let's say instead of 0.4, I set it to 0.6 this time. In this case, we have new actual values and I can again calculate the TP, TN, FP and FN for these and go ahead and calculate the true positive rate, false positive rate, etc. So we see that for each different threshold, I get a different value of TPR, FPR, etc. What I can see here is that instead of changing the model, I can try altering the threshold value and see if the model performance changes. This is called thresholding. We are familiar with how we can predict classes using predicted probabilities. Now the question is, how do we evaluate our model based on that? That's what we'll find out in this video. Let me introduce you to one of my favorite evaluation metrics, the AUC ROC metric. AUC stands for area under the curve. Let's look at some simple examples to give you an intuition about what area under the curve is. Given this curve as shown on the slide, the area under the curve would be this region. Now suppose you have a curve as shown here. Can you guess what would be the area under this curve? It'll be this part, right? Similarly, if you have a curve like this, the area under the curve would be this region. So when we talk about AUC ROC, it is basically the area under the ROC curve. And what is this ROC? ROC stands for Receiver Operating Characteristic. This name comes from signal detection theory that was originally used for distinguishing noise from not noise. And now it's widely used in machine learning as an evaluation metric for binary classification. This metric gives us the trade-off between the true positives and the false positives. Let us look at an example of what ROC curve looks like. So here is an example of the ROC curve. As mentioned previously, the ROC curve gives the trade-off between the true positives and the false positives. This is represented by the true positive rate and the false positive rate. So on the x-axis of ROC curve, we have the false positive rates, and on the y-axis, we have the true positive rates. We know that false positive rate and true positive rate range from 0 to 1. So here on the axis, we have 0 to 1. So you can imagine this as a box of size 1. Therefore, its area will be 1 unit. This is pretty important to keep in mind. Now moving forward, if we make completely random predictions, the ROC would look something like this line here. So the area under this curve would be 0.5, right? Since the total area is 1. So as we understand that the area under the line would be 0.5. Now for a model better than this random model, something like the example shown here, the area under the curve would obviously be greater than 0.5. So that's the intuition behind the AUC ROC metric. In simple words, the more the area under the curve, the better is the model. Now the question comes, how is this curve plotted? Looking at this curve, we can clearly say that we need multiple FPR and TPR values to plot. And in the last video, we saw how changing this threshold can give us different sets of TPR and FPR values. So recall this example we used previously. Here we have the actual values 1 and 0 and the predicted probabilities as shown here. We saw that changing the threshold generated different TPR and FPR values. Now the question is, should we try every value in the range 0 and 1 as a threshold? That's not really practical. So instead, we can set each of these probabilities as thresholds and calculate the TPR and FPR values. So first we will need to arrange these predicted probabilities in descending order. Then we need to take the first value as threshold and calculate the actual values as shown in this table. Once this is done, we can calculate the true positive rate and the false positive rate using the formulas we studied previously. So these three steps will give us one set of TPR and FPR values. We can repeat these steps for the next value. So we can predict the classes by taking 0.9 as threshold, and these will be the classes. Then we can take 0.78 as threshold, and here are the classes. Similarly, we can take it for 0.56, generate the predicted classes, and move forward to calculate the TPR and FPR values. Once we have multiple TPR and FPR values, we'll be able to generate the ROC curve. Now suppose for a particular example, I got the ROC curve something like this. I can calculate the area under this curve, and the area under the curve would be an indication as to how good the performance of my model is. Pretty awesome, right? I have a question for you now. Can you use this metric to compare two models? Think about it. It considers the predicted probabilities for determining a model's performance. But there's one issue with AUC ROC. It takes into account only the order of probabilities. And because of this, we cannot use it to compare two models. And that can often be a big drawback. Let us see why this is the case using a simple example. So here I have the prediction probabilities of two different models already arranged in descending order. Now when we pick the first probability as threshold, we'll have only this value here as 1 and rest all the values will be 0. In this case, when we calculate the true positives and the false positives, the number of true positive, false positive, true negative and false negative will be same, and so will be the TPR FPR values. Again for the second scenario, when we take the second value as threshold and identify the predicted classes, these two values will be 1 and all the values will be 0. On comparing these predicted classes with the actual classes to generate the number of TP, TN, FP and FN, we'll see that they are again same in this case. So the ROC curve for both these models will be exactly the same. And if we calculate the area under the curve, it would look like both the models are equally good. But do you think these models perform equally well? Certainly not. For example, the first model is predicting this class as 1 with 0.94 probability, while the second model is predicting with 0.74 probability. Similarly, for the second scenario here, the first model is predicting with 0.9 probability, while the second model has only 0.69. So we can clearly see that model 1 is able to predict better probabilities for the actual classes. So AUC ROC does not take into account the value of probability, but it only considers the order of the probability, and hence it's not a good metric to compare the different models. So when we are faced with this scenario, we lean on another evaluation metric called the log loss that solves this problem. To put a formal definition to log loss, it is defined as the negative average of the log of corrected predicted probabilities for each instance. Now, what do we mean by corrected predicted probabilities? Let us go back to our example. In this table, we have the actual classes 1 and 0 and the predicted probabilities. If you remember, this was the Titanic dataset. So this column says what is the probability that a person has survived? Or in other words, what is the probability that this ID belongs to class 1? For instance, here the probability of the class being 1 for ID 6 is 0.94. Similarly, for the second, it is 0.9. And if you look at the last row, the probability of ID 5 belonging to class 1 is 0.1, which means the probability of ID 5 belonging to class 0 will be 1 minus 0.1. That's 0.9. So this 0.9 will be the correct probability for ID 5. In order to obtain the corrected probabilities, we consider each observation with the actual value 0 and subtract its obtained probabilities from 1. So here I've done this for all the rows. So you can see that these values are the corrected probabilities. Now that we have the corrected probabilities, we need to calculate the log of these values. And here is the formula for doing that. So when we apply this to our data, the last column shows the calculated log of corrected probabilities. As you can see, these values are a negative. To deal with this negative sign, we take the negative average of these values. So when we do that, log loss comes out to be 0.21 in this case. If I had to summarize all of these steps, then instead of calculating the corrected probabilities, I can change the formula and write it as shown here. Don't be afraid of this formula, it's actually pretty intuitive to understand. Let's look at each component to simplify the matters. Here yi is the actual class and pi is the probability of 1. These I refer the ith row in the data. Now when we calculate 1 minus p of I, this basically gives us the probability of 0. And that is what we were doing when we were calculating the corrected probabilities. So now considering this formula, when the actual class is 1, or I can say when yi is 1, this part of the formula is used while this part vanishes, since 1 minus yi becomes 0. On the other hand, when yi is 0 or the actual class is 0, this whole part becomes 0 and only this part of the formula is activated where we correct the probabilities or calculate 1 minus pi, which gives us probability of 0. So log loss is pretty robust metric for comparing two models, something which AUC-ROC could not do. Evaluating a classification model where the target variable is discrete, like 0 and 1, is still an intuitive process. But what happens when we need to predict a continuous value? How do we evaluate that model? That's what we'll cover in this video. We'll focus on evaluation metrics for regression problems where the target variable is continuous. To give you an overview, we'll be covering these metrics: the mean absolute error, the mean squared error, root mean squared error, root mean squared log error, R squared, and adjusted R squared. We'll cover the first four metrics in this video and the remaining two in the next one. But before all that, it'll be helpful to define what we mean by the term error in this context. I'll pick up an example to explore this. Take a look at this plot. The green line here is the regression line, and these red dots are the actual values. Now, this point here is some distance away from the regression line, so is this point, and so is this. So, this is the error for our model. Error basically determines how far our predicted values are from the actual observed values. Consider these observed and predicted values. So, to calculate the error, I can subtract the predicted from the actual, which means I'm calculating this distance. So, here 28 minus 19 would give me 9, then 33 minus 37 would be minus 4, and so on. That's how the error is calculated. This is for each observation. Now, how do I calculate the overall model error? One of the ways to do this is by taking the average of all of these individual errors. So, how should I do that? We'll first add up all these errors and then divide by the total number of values. But if you notice in this case, we have some negative errors and some positive values. So this will effectively cancel each other out. And if you take a sum, it will come out to be 0. That didn't help, right? So what else can we do to calculate the aggregation? As you know, that one of the problems is that we have some positive and some negative values. These positive and negative signs denote the direction. So for example, for this error, it will be positive sign, then for this, it will be negative, here it will be negative, and here it will be positive, and so on. So we can remove these directions and take only magnitude into consideration. One way of doing this is by taking the sum of absolute values and then calculating the average. This is called the mean absolute error. So here we are taking the average of the absolute values. So the negative sign disappears. For our previous example, the absolute values of errors come out to be as given here. Now when we calculate the mean absolute error, it comes out to be 5.6. A second method to remove the negative signs could be taking a square of this difference. While taking the square, all of these differences will be positive, and so the sum won't turn out to be 0. This is called the mean squared error, or MSE, and here is the formula. But one problem with mean squared error is that since we are taking the square of the errors, it changes the unit. Let's go back to our previous example. Suppose I have these values in meters. So let's say the actual value is 19 meters, 37 meters, and so on. Now when I calculate the error and take a square, the unit goes to meter square. So if I calculate the mean squared error in this case, it comes out to be 34.4 meters square. This doesn't precisely represent our error, right? And this happened because we just took the square of the errors. So to compensate this, we can take a root of this error and we'll be back to our same unit as the target variable. This new metric is called the root mean squared error, or the RMSE as it's commonly known. So for the same example, when I calculate the RMSE, it comes out to be 5.86 meters. RMSE is one of the most commonly used evaluation metrics for regression problems. You'll encounter this quite often in data science hackathons as well. But note here, even RMSE might not be the best metric for regression problems. Wondering why? Let me illustrate this using a simple example. So suppose I have these two cases. In the first case, my actual value is 1 and predicted is 401. Something has clearly gone wrong in our model. In the second case, the actual value is 10,001 and the predicted is 10,401. That's a pretty decent performance by the model. Now, if I calculate the RMSE for both cases, it comes out to be 282. That's right. We have the RMSE for both cases equal. This is because the RMSE considers only the difference between the observed and the predicted values. And the difference in both the cases, as you can see, is the same, 400. So if we can't use RMSE in these problems, what can we do? Now, instead of directly taking the average of square errors, we can take a log of the values and then take the average of square of the errors. Using log basically scales down the larger values. This metric is called the root mean squared log error or the RMSLE. So for the same example we saw in the last slide, the RMSLE in the first case is 2.65, whereas in the second case it's 0.0014. It's a far better metric, right? Since we now know that this model is performing decently well while this is very bad. That's a much more practical explanation of the errors. We learned what the RMSE and MSE values are. We also saw if the RMSE decreases or the MSE decreases, the model's performance will improve. But these values alone are not intuitive. Why? Let's take a small example. In case of classification problem, if the accuracy is 0.8, we know how good our model is against a random model, the accuracy of which is 0.5. So the random model here can be treated as a benchmark. But when we talk about MSE or RMSE metrics, we do not have a benchmark to compare. So is there any metric for regression where we can compare our model against a benchmark model? Yes, there is. Recall the mean squared error concept we discussed in the last video. Here, we simply take the average of sum of square errors. Now, instead of using the MSE value alone, we can look at it with respect to the baseline model, which means we should divide the MSE of model with the MSE of baseline model. Now, what is a baseline model? It is basically the MSE when the predicted values are simply replaced by the mean of all values. As you can see, the 1/n in numerator and denominator cancel each other out, so we are left with the sum of squared errors, which is called the relative squared error. A few important things to note here is that when the MSE of model and MSE of baseline model is equal, in that case, this value is 1, which means our model is as good as predicting the average for all the values. If this value is more than 1, we can say that our model is worse than the baseline model. As you might have guessed, ideally this value should lie between 0 to 1. Now when MSE decreases, this whole value decreases, and we can say that the model performance has improved. So lower this value, better our model, which is quite contradictory to the general idea that higher values are better. Is there any solution to this? Well, here's the trick. Simply subtract the relative squared error, which is this term, from 1. This new metric is called the R squared. So when the MSE decreases, this whole value decreases, which means we are subtracting a smaller value from 1, and in turn the R square will increase. So better the model, higher will be the R square value. But there's a big problem with R square. When you add more features to the data, the value of R square either increases or does not change. It never decreases regardless of how any feature impact the model. So we are not penalized for any random or unimportant features that we add. It's a very inefficient way of building models. To deal with this issue, we have a better version of R squared, and it's called the adjusted R square. Here's the formula for adjusted R square. N here is the number of samples and K is the number of features. As you can see, this metric takes the number of features into account. So now when we add more features, this term in the denominator would increase, which means the whole fraction increases. Now, if adjusted R square increases significantly, the change in this fraction can be compensated. But if this term increases and R square does not change, in that case, we are subtracting a larger value from 1, and so the adjusted R square would decrease. So now we have a metric for regression that compares the model with a benchmark and provides a score between 0 and 1. That was all about R square and adjusted R square. Thank you.